Hello students, we'll further dive into the implementation issues of pipelining. A quick recap of what we have seen so far. We have started addressing each of the assumptions that we made in the ideal pipeline. The first assumption was to uh, decide where to keep the unfinished instructions. Accordingly, we introduced the interstage buffers or the pipeline registers. The second one was assuming that all the tasks of the pipeline, all the stages of pipeline will take equal amount of time, and that might not be possible all the time. So accordingly, we need to adjust the clock cycle or find some workaround. The third one is assuming that there is an exclusive hardware for each of the stages, but we saw that it might not be the case. Those events are called structural hazards. Accordingly, we have introduced a faster register file which will work twice as fast as the other pipeline stages, and we also split the instruction and data memories so that they can be accessed independently during the fetch and memory access stage, right? And the fourth assumption was uh, that executing one instruction is totally independent of another. That is hardly the case. So we've started addressing what's called the data hazards. Basically, if there is data dependence between instructions, how do we handle that? Um, as part of hardware solutions, we looked at stalling and data forwarding. And in the previous class, we looked at the software solutions, which would be inserting no ops or, if possible, rearrange the instructions to reduce the number of stalls or bubbles in the pipeline, right? In this lecture onwards, we are going to look at the control hazards. The fifth assumption is ignoring the extra hardware to manage all the stages independently, right? So that we are no longer oblivious. We started looking at each of the impact of each of the above decisions that we made, right, on the hardware. Now let's dive into the control hazards. Basically, control hazards will be resulting because of control dependence among the instructions. Control dependence will determine the ordering or the execution of instruction, say P, with respect to another branch instruction, say B, right? What it says is P should be executed only when it needs to be executed, not all the time. Means based on the outcome of branch B, we should decide whether to execute P or not. A quick example to correlate. Let's say the instruction B is a simple if statement, right? And let's say instruction P is part of that if block, and let's say we are calculating C equals to A plus B, right? And the else part is where we are having instruction Q, wherein we are calculating A minus B and placing it in another variable C. A very high level example here. Now what control dependence says is whether we have to execute P or not is dependent on the condition check that we do in the if condition, which is the branch instruction, right? So if the condition fails, only then we execute P, but if the condition satisfies, if the condition satisfies, then we execute P. If it doesn't, then we execute Q. So we would say that P and Q are dependent on B. This kind of dependence is called control dependence, right? Control dependence need to be preserved. That's quite obvious, to preserve the program order. Program order, in the sense, the correct execution of the program will happen only when we respect the control flow, right? There are two main constraints that the control dependence imposes. What are those? The very first one is we cannot move P uh, anywhere we would like. Let's say here in the previous example, P was after instruction B, right? We cannot just rearrange and place P before B, what it would result is P will execute no matter the result of B. That is a violation of control dependence. Or the other way around. Let's say there is some instruction X before this branch instruction. So X should ideally be executed whether independent of the result of B, right? But if we want to, if we try to optimize and let's say we place X below after the branch B, what it means is now the execution of X is dependent on the result of B. Again, this is a violation of control dependence. Basically, we are introducing an additional control dependence which was not there in the original program. So both of these things should be carefully avoided. Let's look at some of the examples here. Right, let's say we have three instructions, add x2, x3, x4, and the second instruction is beq x0, x2, l1, and the third instruction is, let's say, lw x1, 0, x2, and for after that we have the instruction with label l1. Right, now the very first thing we would notice is there is a control, there is a data dependence between instruction add and beq. Add is the producer and BEP is the consumer. Let's say we have already dealt with that somehow. We'll try to focus on the control dependence here. Here, the instruction at L1, label L1, and the instruction LW are dependent on the outcome of BEQ, right? So, of course, L1 will get executed either way, but the instruction LW should be executed only when the outcome of this branch is not taken, means we are not taking L1, right? So if we try to move LW before BEQ just to optimize and to see and reduce number of stalls, what happens is the execution of LW will no longer be dependent on BEQ. That can potentially result in some unexpected results, right? Unexpected events which are called exceptions. I'm going to deal with exceptions a little more in detail after a couple of lectures, but for now just assume that exception is a corner case which is stalling the pipeline indefinitely. For example, divide by zero error, right? When you try to compile your program, nothing happens, but when you try to run the program and somewhere there is a calculation that you do where the denominator is zero, the program execution would stall and it would give an error saying that you are trying to divide it by zero. So those kind of events can be termed as exceptions. So if we move the instructions without understanding the dependence among them, then there is a potential scenario where new exceptions will be created. Now here, what is the possible new exception is the memory protection exception. Let's try to understand this instruction here, BEQ x0, x2, L1. So what we are saying here is if x2 is equal to x0 means 0, then jump to L1, otherwise load from the location x2, right? Now if I have placed this above, what we effectively it would mean is even if when x2 is 0, we are trying to load some value, let's say that location does not belong to us, that would potentially result in memory protection exception. Another example in similar lines, so let's say we have add x1, x2, x3, BQ x0, x4, L, then we have subtract x1, x5, x6, then we have some instruction at label L and some OR instruction x7, x1, x8, right, and so on and so forth. Now if we try to look at the data dependence, we have data dependency between add and OR and subtract and OR, and which one of these dependents would come into the picture will be determined by the BEQ, right? If the value in x4 is 0, then we would directly jump to L, and it would mean that the value x1 here is the outcome of add instruction. But let's say if BEQ check of x0 and x4 is failing, it would mean that x1 is x5 minus x6. That's what would be used in the OR instruction here. So even though the the registers that we have used in the control instruction are not same as the other instructions, it potentially determines how the data flow will happen in the program, right? So if we violate, and let's say if we overlook that and move the subtract instruction before this, before the BEQ, it can potentially result in wrong data flow, means your program can give wrong result, undesirable result, right? So again, this is an example of control dependence where the dependency is not so apparent like in example 1, because the register values are quite different. Now let's look at a little more tricky case. Let's say we have add x1, x2, x3, BEQ, x12, x0, and label is skip. And following that, we have subtract x4, x5, x6, add x5, x4, x9, and after somewhere after this instruction with label skip, we have an OR instruction x7, x8, x9. Right now, let's assume that the value x4 is not being used inside this skip, means after the instructions in the skip module, let's call it that way, right? Can we move the subtract instruction now? Yes, potentially yes, because the subtract instruction might is not being used in the target also, right? Target of this branch. So we can probably move the subtract instruction before the BEQ. So even if we do not jump, what happens is the add instruction will continue to execute. But if even if we jump, there is no problem because the skip module is not using it. It looks a little okay when compared to example 2. But what we need to take additional care is the add instruction is dependent on the result of subtract instruction. Here there is a producer consumer relationship. Now when we move the subtract instruction before BEQ, right, what happens is there is a chance that the value in x5 is not correct when the branch is taken, and when the branch is not taken, the value of xy will vary. Again, this is not a desirable scenario. So the compiler needs to be extremely careful to figure out all these dependencies. We have seen in the previous lecture how it can try to figure out some data dependencies through registers, right, among the instructions, but the control instructions add more complexity to its analysis. So a key point to remember from control dependence is we need to understand the exception behavior of the program, and if at all we are trying to reorder the instructions, we should take care that no new exceptions are getting introduced or none of the earlier exceptions are missing in the modified program. And the second point is the data flow should be maintained, otherwise the end result of the program will be wrong. So because the branches make the data flow dynamic, we need to handle them very carefully. So considering all these, we can say that the compiler has very limited scope to handle control dependency, right? But we are going to look at a couple of methods what the compiler can do. But before that, we are going to dive into the hardware optimizations on how we can handle control dependence. Like I mentioned earlier, some of the control dependencies can result in control hazards. Let's try to understand what a control hazard is. Before that, a quick uh, status quo. What we have looked so far is pipelined execution of sequential instructions, but now we are looking at pipelined execution of sequence of instructions wherein we have the control instructions also. Because the control instructions have the capability to change the flow of instructions, right? The pipelined execution has some additional difficulties. We are going to understand them. Before that, a few new terms that I'm going to introduce you to. The first one is branch taken. What it means is, as the name says, the branch instruction is taking or going to the target address, is taking the target address as its next PC. What it means is the condition we have put in the branch is satisfied. When we look at the unconditional branches or jumps, they are always taken because there is no condition check at all. We always go to the target location. Branch not taken, it's the other event wherein the branch condition is not satisfied, and what we do is we go to the next sequential instruction. So PC becomes PC plus 4 ideally, right? Branch target address, like I already mentioned, is the location that the control will go to if the branch condition is satisfied, or when we look at a jump, we always go to the target address. And how is it calculated? The immediate field in the branch or jump instruction is taken, that will be added to the PC appropriately, and it will give us the target address where to go to or where to jump to. We have the terms forward branch and backward branch. So as the name says, forward branch meaning the target of this branch is somewhere below. It means that the immediate field in the target in the branch instruction is having a positive value, means we add this positive value to the current PC and we go to some location below the branch instruction. This scenario is called forward branch. If the immediate field is negative, what it means is we are going to jump to some location which comes earlier to this particular branch instruction. So we are going to say it's a backward branch. The term branch penalty or branch hazard or control hazard is basically the delay we introduce in the pipeline to handle the control dependence. Okay, now let's try to understand them further. For that, we need to understand or we need to go back and see where or how the branch execution happens in stages. Let's try to answer the question, when is the branch result determined? Means when is the branch getting resolved? So this would typically happen in the execute stage. Let's say we give BEQ x1, x2 and some label L1, right? The value in x1 and x2 will be supplied to the execute stage and they will be compared, and based on that comparison we need to decide whether to go to L1 or whether to continue with the next instruction, right? So that is the answer for the second question. When does the new PC gets decided? The branch result gets determined in the execute stage, and the new PC gets decided if we can optimize in the execute stage itself, or we might even end up doing that in the memory stage, because the new PC calculation is handled by the instruction address generator, IAG. This is with respect to the branch instructions. Now let's look at the jump instructions. When is the branch result determined? Basically, when do we know whether to jump or not? For jump, it is unconditional. So the moment we know that it's a jump instruction, we will know that we have to take the uh, target address, right? So this would happen in the decode stage itself. And when do we know the next PC? Basically, the moment we know that it's an unconditional branch or jump, we can add the immediate value to the PC and compute the branch target address, right? So that can potentially happen in parallel with the execute stage by the instruction address generator. So for branch, the result potentially is determined in the execute stage, and the new PC can be calculated in the very next stage itself by the IAG. Now, when it comes to the jump, the branch result or the branch outcome, because it's a jump instruction, is known at the right in the moment we know that it's a jump, basically in the decode stage. And when we know that it's a jump instruction, we can calculate probably in the very next stage, the next PC. Okay, with these things in mind, let's look at the pipeline execution of control instructions with some examples. So here is my timeline, cycle 1, 2, 3, 4 through 8. Let's say my first instruction is JL X1 I10. So it will be fetched in cycle 1, decoded in cycle 2. That's when we will know that it's a JL instruction. At the same time, we are going to fetch I2. Let's say it is AND X12, X2 and X5, right? Uh, by the end of cycle 2, we know that it's a JL instruction, and in cycle 3 we are going to calculate the new PC. Basically, the immediate field in JL instruction will be added to the next PC, and we will know where to jump to. But in cycle 3, what happens is we are going to decode I2 and fetch I3. Only at the end of cycle 3 we realize that we should not be executing I2 I3 in that sequence, but rather we should jump to I10. So what happens is in cycle 4, uh, when we know that the target is I10, we have to flush or clean the pipeline basically of I2 and I3. That's called flushing the pipeline, right? What basically flush means is we are going to zero out all the interstage buffers between the fetch and decode stage, and we are also going to zero out the value in the instruction register in cycle 3, and the new PC value will be given in cycle 4. So when I1 enters the memory stage, at that point we will fetch I10 and continue the execution further. So what happened is, because of this particular control instruction, we had to flush the pipeline of instructions I2 and I3, potentially introducing two bubbles in the pipeline. These two bubbles can be counted as branch penalty, or the here it's a jump penalty. Now, hardware designers thought about how to improve it, and accordingly they came up with a intuitive idea, just like data forwarding. What they said was, because we know that uh, the instruction is either JL or JLR in the decode stage itself, why don't we compute the next PC calculation in the decode stage itself? Because anyways, it is being handled by instruction address generator, right? So again, with that in mind, let's look at the timeline. What happens? So in the very first cycle, I1 will be fetched, decoded in cycle 2. That's when we will know it is JL also, right? And in the meantime, we go ahead and fetch I2. But right after second cycle, we will know that it's a JL instruction, and we would have computed where to jump to. The I1 will progress to execute stage. Ideally, I2 should go to the decode stage, but we are going to flush it out because we realized that by the end of cycle 2, it is a jump instruction and the target location is I10. In cycle 3, we are going to uh, fetch instruction I10, the target location of this particular JL instruction, right? And we are going to make a progress further. So here, with this small optimization of allowing the instruction address generator to give us the target address in parallel with the decode, right? We are able to save one cycle. So earlier the branch penalty was 2 cycles, now it became 1 cycle. So it's good. We made 50% improvement in the control hazards, right? But can we do better? I will leave you to think about it. Let's take the example of branch instructions and see how they can be handled. Again, we have the timeline, cycle 1 through cycle 8. Let's say our first instruction here is BEQ x2, x1, x10. What we expect to happen is if the value in x2 and x1 are equal, then the next instruction that needs to be executed after I1 is I10. Let's see how we can achieve that in the pipeline fashion. So in cycle 1, I1 will be fetched, I2 will be, I1 will be decoded in cycle 2. At the same time, I2 will be fetched. In cycle 3, we are going to execute the branch instruction. At the same time, we are going to decode I2 and fetch I3. Only at the end of cycle 3, we will know whether the branch needs to be taken or not. Basically, the values in x2 and x1 will be compared, and if they are equal, we need the new PC will be calculated, saying that use the immediate value in I1 and add it to the current PC, right? So because the branch decision is known only in cycle 3, and let's say if the branch is taken, it means that instead of executing I2, I3, etc., we need to execute I10. We need to flush both I2 and I3, and in cycle 4, when I1 moves to the memory stage, I10 will be fetched in cycle 4 and the execution will further continue. The main hindrance we have here, unlike the branches, unlike the jumps, was we will not know whether to whether to jump to the target location or not, because the values of x2 and x1 are compared in the execute stage. So accordingly, we have 2 cycles of branch penalty. Again, the hardware architects wanted to reduce it. So as a direct extension of how we dealt with the branches, the idea they proposed was, why not move the branch decision logic also from the execute stage to the decode stage? We have already said that the branch target, instead of being calculated in parallel with the execute stage, will be done in the decode stage. Now we are saying that the branch decision logic, basically comparing the registers, right? In RISC we have branch if equal, not equal, greater than equal to, or less than, right? So all we need is a comparator. We will move that comparator from the execute stage to the decode stage. What happens if we are able to do that is, in cycle 1 we fetch I1, it will be decoded in cycle 2. Right at that time, at that moment, we will know that it's a branch instruction and that values x2 and x1 are being used, right? At the same time, we know that we will be fetching I2. At the end of cycle 2 itself, we will know the outcome of comparison of values in x2 and x1, because we have moved the comparator from the execute stage to the decode stage. What happens ideally is In cycle 3, I1 moves to the execute stage, I2 would be moving to the decode stage, but because we resolved the branch in the decode stage itself, and we realize that let's say the branch is taken here, we need to go to I10. So we will flush the pipeline, meaning we will zero out the interstage buffers between fetch and decode, and we'll update the PC with I10, right? In cycle 3, when I1 is in its standard execute stage, I10 will be fetched. And in cycle 4, I1 moves to the memory stage, I10 will be decoded, so on and so forth. So earlier we had 2 cycles of branch penalty. Now we were able to reduce it to 1 cycle. What we did was we moved both the branch target calculation and branch decision making to the decode stage. Again, I will leave you with the thought, can we do any better? It's really good that we reduce the penalty from 2 cycles to 1 cycle, but can we do any better? We have very interesting optimizations that were proposed to answer this question. Before that, let's try to see what is the penalty at the hardware to reduce these 2 cycles to 1 cycle. The additional hardware that is needed is, either way we need the flush logic, right? We can instead of flushing probably think about stalling the pipeline, but it is too trivial and it does not help us in the performance, because either we are flushing or stalling, there will be a bubble in the pipeline, right? And we cannot keep flushing or stalling because the branches typically occur very frequently in our programs. We have a lot of loops and if statements, switch statements, etc., right? So few standard programs which we call benchmarks were studied, and they reveal that for every 100 instructions, 25 instructions are branch or jump instructions. What it means is there is a potential uh, scenario wherein 1 or 2 cycle stall will be there for every 4 instructions. So that is a huge drop in the performance. So we cannot simply be happy with flush and stall. So we have moved some additional, we introduced some additional hardware into the decode stage, basically the comparator. So with that, we are able to reduce the penalty from 2 cycles to 1 cycle. Also, we said that the instruction address generator will be giving us the new PC value, excuse me, right at the end of decode stage itself. So in order to make this happen, now we need to introduce some new forwarding paths also. Earlier, the values we wanted need to be uh, given to the execute stage and the memory stage. But now, because we are resolving the branch in the decode stage, if there is a data dependency between instructions which uh, the branch instruction and any of the instructions before it, that value also needs to be forwarded. So we need additional forwarding logic from end of execute stage to the beginning of the decode stage, and end of memory stage to the beginning of decode stage, right? So this all additional hardware are needed that would effectively help us to reduce the branch penalty from 2 cycles to 1 cycle. We are going to dive further into optimizations that handle the control hazards even better, right? But I will pause for now. Thank you.